Hi friends, I am Francis Xavier Rajan, Assistant Professor, Mechanical Department of Mechanical Engineering in the College of Christian College of Engineering and Technology, Pottanjatram. Now, in this session, we are going to see about the topic Venturimeter. Venturimeter, before entering into the Venturimeter, let us see the introduction of the Venturimeter. Venturimeter is a topic comes under fluid mechanics. Fluid mechanics means it is a branch of physics which deals with the studies of liquids and gases and the forces acting on them. It branches about two, that is fluid statics and fluid dynamics, and the studies of engineering, geophysics and in biology. Mainly this Venturimeter concentrate on pressure, viscosity, Bernoulli's principle, the conservation of mass, energy and momentum. Okay, this is the introduction part, and now we can move on to the topic Venturimeter. Venturimeter is a device used for measuring the rate of flow of a flowing fluid. Whatever may be the fluid, we can measure the rate of flow by means of how Venturimeters. These are the versatile solutions in that their length can be changed to fit a defined space, and they can be modified to provide the rate of flow or to calculate the rate of flow or measure seepage. They can be used reliably and they can be used for rectangular and circular fittings. Venturimeter, the main parts of the Venturimeter consist of three parts. First one, the left side end, that is a sharp converging part, and then second one in the middle part, this is the throat part, and the third one is the diverging part, and this is the right end part. These are the main components of the Venturimeter. Here, in that first one, there's a sharp converging part. It is the portion of the Venturimeter where the fluid gets converges. And in the second part, the throat, it is the portion that lies in between the converging and diverging part of the Venturi. The cross section of the throat is much less than the cross section of the converging and the diverging parts. That is, the throat part is the smallest part in the Venturimeter. As the fluid enters in the throat, the velocity increases and the pressure decreases. And then the last part is the diverging part, where from the throat the fluid enters into the diverging part and the flow occurs. And in coming to the properties of the Venturimeter, first point is the discharge. It is used to find or determine the discharge coefficient value. Second one is the shape of the coefficient, and the installation sensitivity for both upstream and downstream conditions, tap location sensitivity, head loss across the profile, accuracy and repeatability, then applicability for liquids, gases, slurries, sludge, mixed media and varying viscosities must be determined and proven. Then coming to the principle of Venturimeter, it works under the principle of Bernoulli's theorem, Bernoulli's equation. This Bernoulli's equation states that in a steady ideal flow of incompressible fluid, the total energy at a point of a fluid is constant. The total energy consists of pressure energy, kinetic energy and potential energy or datum energy. And this statement is mathematically converted to as pressure energy plus kinetic energy plus potential energy or datum energy equal to a constant. That is, the pressure energy is P by rho g plus kinetic energy is V square by 2G plus the potential energy is Z equal to a constant. That is the Z is a datum energy. Here all the energies are taken per unit weight of the fluid. Then the statement of the Bernoulli equation, that is we are considering section 1 and section 2 means in a pipeline means P1 by rho g plus V1 square by 2G plus Z1 in the first section, that is equal to P2 by rho g plus V2 square by 2G plus Z2. Here, how it works? Venturimeter, how it works? The venturimeter is used to rate measure the rate of flow of a fluid flowing through the pipes. Here, we have discussed two cross sections. First at the inlet and second one is at the throat. The difference in the pressure rates of these two sections is used to calculate the rate of flow through venturimeter. Here, this is the schematic diagram of the venturimeter. Here, the first section is the convergent part, and this one is the throat part. In the middle is the throat part, and the third one is the divergent part. In the first section, under the throat section is connected by an inverted U-tube. There, with the help of that inverted U-tube, the difference of height level of a fluid, which helps to find the rate of flow of a fluid. Okay. As the water enters into the inlet section, that is, in the converging part, it converges and reaches to the throat. In the convergent part, converges and reaches into the throat. In the throat section, there in the throat, its velocity gets increases, and due to increase in the velocity, the pressure drops to the minimum. Here, in the throat section, the velocity gets increases, and the pressure goes to minimum. But in the section 1, the velocity is decreases and the pressure is the maximum. At the section 2, the velocity of the fluid is maximum and pressure is minimum. The pressure difference at the two sections can be seen in the manometer, that is the inverted U-tube manometer attached at both the sections. This pressure difference is used to calculate the rate of flow flowing through the pipe. Now we can see the expression for the rate of flow for venturimeter. Let us consider, D1, P1, V1 and A1 are the diameter of the inlet, pressure at the inlet, velocity at the inlet, and area of cross section at section 1. And D2, P2, V2 and A2 are the corresponding values at the section 2. Then we are applying the Bernoulli equation at section 1 and 2. We have P1 by rho g plus V1 square by 2G plus Z1 equal to P2 by rho g plus V2 square by 2G plus Z2. As the pipe is horizontal, that is, as the pipe is horizontal means the datum height between the sections 1 and 2 is the same. So we are equating Z1 and Z2. So Z1 and Z2 values are 0. So we are neglecting Z1 and Z2. Therefore, P1 by rho g plus V1 square by 2G equal to P2 by rho g plus V2 square by 2G. Then, by simplifying this equation, P1 minus P2, that is, P1 minus P2 by rho g equal to V2 square minus V1 square by 2G. Here, P1 minus P2 by rho g is the difference of pressure rates at section 1 and 2, and it's equal to H equal to P1 minus P2 by rho g. Substituting these values of H in equation 1, we have H equal to V2 square minus V1 square by 2G. Now applying the continuity equation, that is the second concept, continuity equation at section 1 and 2, we have A1 V1 equal to A2 V2. From this equation, that is A1 V1 equal to A2 V2, from this we are taking V1 equal to A2 V2 divided by A1. Substituting the values of V1 in the equation, in the above equation, that is from the Bernoulli equation. Substituting these values of V1 in equation 2 and solving, we get V2 equal to A1 by square root of A1 square minus A2 square into square root of 2GH. And finally, we have calculated the rate of flow, that is discharge Q equal to, the general equation is Q equal to A2 into V2. Substituting the values of V2 in the above equation, that is Q equal to A1 into A2 divided by square root of A1 square minus A2 square into square root of 2GH. Q is the theoretical discharge under ideal conditions. Actual discharge will be less than the theoretical discharge. The actual discharge is given by the formula Q actual equal to CD, that is CD means coefficient of discharge. Coefficient of discharge value is maximum is 1, that is in between 0.9 to 1. That is the theoretical value. A1 into A2 divided by square root of A1 square minus A2 square into square root of 2GH. CD is the coefficient of Venturimeter and its value is less than 1. So this is the 2D diagram of Venturimeter with the connection of inverted U-tube manometer. See the pressure difference between the pipe flow, that is H. With the help of H, we are going to calculate the rate of flow in the Venturimeter. Here is the graph represents the difference between the pressure and the distance, where it gives the pressure loss from convergent part to the throat part. And then advantages, Venturimeters are the versatile solution in that their laying length can be changed to fit a defined space. They can be modified to provide rate of flow control or measure sewage. This Venturimeter can be connected in any type of pipe flow. That means which is a horizontal pipe or a vertical pipe or a cross-sectional pipe or an inverted pipe, or in any area we can use this Venturimeter. Venturimeter can be oriented in any plane and can measure accurately whether the line fluid is flowing upwards or downwards. Venturimeters have no moving parts and can function reliably and accurately for decades, with some examples in service for more than 100 years. Significant benefits of the Venturimeter is that the design can be modified to fit almost any requirement, and it can be constructed with a broad range of materials depending upon the applications and matter that will be measured. And there are two versions in particular that have made significant impacts on Venturimetering: the modified short form of Venturimeter and the insert Venturimeter. In public water supply systems also we can add the Venturimeter. That the schematic diagram of this layout diagram of this Venturimeter is shown. That is from source and then from reservoir and then Venturimeter, then treatment, then pumping station, then distribution. Finally, with the help of Venturimeter we can find the rate of flow, and if we need we can reduce the rate of flow, or if we need we can increase the rate of flow depending upon the liquids or gases used in the pipelines. Especially these Venturimeters are helpful in the gasoline pipes. Thank you.